Good morning, everybody. Welcome to our Physical Sciences program for this morning. It's very nice to have all of you in attendance, and we want to extend a special welcome to all those at Inkwenkwezi High School, at Voorbrug High School, as well as at Florida High School. Grade 12s, thank you very much for joining our program this morning. We're really going to learn a lot. And we know that this is going to help you as you prepare for your final examination that is going to take place in a few days' time. We also want to say welcome to the teachers who've joined us as well. We know you've done a lot of work during the year, and now we have a program which is going to revise a very important topic that is taken up in paper 2. And as you can see from the monitor, we're going to be talking this morning about chemical equilibrium. Now, you know, for many learners, chemical equilibrium presents many challenges. What we want to do today is we want to come to an understanding in connection with chemical equilibrium. Okay, so if I can just take the monitor and let me just go back to, let's see how I can just advance this nicely. There you have it. Okay, and I go back to the screen. All right. Now, in understanding chemical equilibrium, the first important thing that we need to recognize is that there are two types of systems that we need to differentiate. If you notice on the monitor, the first one is called an open system. Look at this picture here. Here we have a beaker, and this beaker has a liquid inside. But notice there is no lid on the beaker. What is happening here? Well, matter and energy can leave the system. It can escape. So therefore, no equilibrium will be established in this particular system. This is what we call an open system. What about the contrast of that? Well, look at this diagram here. Here we have a beaker. We have the liquid inside, but notice there is a stopper or a lid on top of that beaker. Matter and energy cannot leave the system. This is how, for a closed system, a dynamic chemical equilibrium will be established. And how is a dynamic chemical equilibrium established? Well, it is formed, as you can see, when the rate of the forward reaction and the rate of the reverse reactions are equal. Now we need to talk about this term reversible reaction. Many chemical reactions are reversible, and reversible reactions are indicated with a double arrow in a chemical equation. If you look here at this particular slide here, there we see the double arrow right here. Let me just get the mouse. It's the double arrow, and then there's the double arrow here. Notice the top one represents the forward reaction. The bottom one represents the reverse reaction. And so here on the diagram here, as you can see on this piece of paper, if I had to draw the forward reaction, there's the reaction going in this direction here with an arrow there. And the reverse reaction will be exactly the same, but the arrow will be going in the opposite direction there. This is how we represent a reversible reaction. Take note, the one go on top is the forward reaction, and the one at the bottom is the reverse reaction. We do not talk of forward and backward. No, we talk about forward reaction, and then we talk about reverse reaction. Those are important concepts that we need for our lesson today. Moving on, the forward reaction, as you can see from the monitor, is one in which the reactants change into products. Now, from grade 10 and into grade 11, your teacher obviously told you that what is on the left-hand side of your chemical equation represents your reactants. So in this case, here we see 2 hydrogen plus 1 mole of oxygen. These are the reactants. There we have our reversible reaction. We've just established that. And now here we have 2 moles of water. So water on the right-hand side represents the products that are formed by the reactants reacting with one another. Notice for the reverse reaction, products will change into reactants. Okay? So in other words, the water, if it has to go back, will change into hydrogen plus oxygen. That is an example of the reverse reaction. What about chemical equilibrium? When is a system going to experience chemical equilibrium? Well, as the monitor indicates, a system is in chemical equilibrium when the rate of the forward reaction and the reverse reaction are equal. Look at this diagram. Here we have the rate indicated on the y-axis, that's our dependent variable, and here we have the time on the x-axis, which is the independent variable. But now look at the graphs. The dotted line represents the forward reaction. Notice it starts there and it comes down, 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 and then it almost comes to a plateau. In other words, it's starting to go flat. What about the reverse reaction? Well, it starts from almost nothing and it comes up, up, and it meets that one there. And together here. So as it says here, the rate of the forward reaction and the reverse reaction are equal. For a system to experience chemical equilibrium, that is a very important point. The rate of the forward reaction must equal the rate of the reverse reaction. Also, the concentration of the reactants and the products should remain constant. And this is what is indicated here on the monitor too. And by means of a graph, notice this graph now. This graph is a graph of concentration and time. Notice the reactants. There's the reactants there. The concentration goes up, 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 and there it starts coming to a flat part, the plateau, one can say. And what about the products? Well, there we have dotted lines down like that, and we can see that these two are almost parallel, right? So in other words, the concentration of the reactants and the products are constant. When we see them reaching these parallel planes, then we know equilibrium has been established. What factors favor a change to the equilibrium position? Well, you probably learned during the course of the year that certain factors can change a system in equilibrium. In fact, they affect the concentration of the reactants or the products. The change disrupts the equilibrium, causing the rate of the forward or the reverse reaction to either increase or decrease because the system has to establish or come to a new equilibrium. So, what are those 3 factors? You've got your notes there, and there is space for you to make notes as we're going along. Please make a note of these important points. There are 3 main factors. Firstly, changes to the concentration at constant volume, and this only applies to aqueous solutions and to gases. So if you got that point, the first one, changes to the concentration of aqueous solutions and gases. Next, change to the temperature. Now, when the temperature is increased, the endothermic reaction is favored. And when the temperature is decreased, the exothermic reaction is favored. So if you got that point, changes to the temperature. What is the third factor that affects equilibrium? You guessed it. I could hear you actually saying it. The pressure. Well done. And pressure only applies to compounds in the gaseous phase, or to gases, one can say. So have you got those 3 main points? Factors that affect equilibrium position. Number 1, concentration. Number 2, temperature. And number 3, pressure. And if you're looking for an acronym, right, because you're in your study phase, just remember TCP. T for temperature, C for concentration, P for pressure. Those are the factors that affect the equilibrium position. Now, the French, have always been interested in chemical reactions. In fact, they've done a lot of experimentation over the years in chemistry. And you may know some very famous chemists. But there was one in particular, a gentleman whose surname is Le Chatelier. What he did is he studied chemical reactions in a very in-depth way, not just the forward reaction and the reverse reaction, but he actually came up with a principle that he formulated for his studies and for his discoveries, one can say. And that principle is with us today. We know it as Le Chatelier's principle. How does Le Chatelier's principle play off in connection with chemical equilibrium? Well, if you notice the monitor, there we read, Le Chatelier's principle helps to predict how the system will respond to the changes made to an equilibrium system. And so in a very real sense, we can say that Le Chatelier's principle states, if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce the change. Very important. If a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce the change. Now, let's understand Le Chatelier's principle more. In other words, we need to go deeper into what this really means for us. Well, basically, an equilibrium system will respond to reduce the effect of the change by favoring either the forward or the reverse reaction. For example, a factor causes a change to an equilibrium system, increasing the concentration of the reactants. So the situation is very much like what we see on monitor there. Suppose we have a seesaw. This side here has got the heavier mass, one can call it, because it's down there, right? You can imagine two people on here. This person, this side is very heavy, that person is very light. And so in terms of our chemical equation, and certainly our chemical equilibrium, well, notice this represents the reactants. The rate, the forward reaction is increased. And notice this side is heavier because the reactants increase. Well, this side needs to be balanced, the other side. So in other words, the reverse reaction, the rate is decreased. That side represents the products. In response, the forward reaction is favored. In other words, it increases, and the reverse reaction decreases, restoring the balance, right? So I think you can see that because this side is heavier, this side here will be favored so that there is an equilibrium between both sides. This brings us to our next important concept, and that is the equilibrium constant, oftentimes called the Kc constant. And as you know, we are heading for Kc calculations, which is really the bedrock of our lesson this morning. The equilibrium constant, Kc, is the ratio of products to reactants. And as you know from mathematics, whenever we talk of a ratio, we're talking of division. Something is in the numerator, something is going to be in the denominator. So what is in the numerator? Well, the concentration of the products is always in the numerator. What is in the denominator? The concentration of the reactants. And this is basically what we are going to establish this morning. You see, the equilibrium constant, as you can see on the monitor, allows a chemist to determine the progress of a reaction, indicating whether the formation of the reactants or the products is being favored. Have a look at this hypothetical equation. We say hypothetical because the A, B, C, and D are not representative of any compounds or elements on the periodic table, and the small a, small b, small c, and small d represent the number of moles. So, for example, if we have a chemical equation that looks like this, notice it's a reversible reaction. The equilibrium constant for the chemical reaction at equilibrium of this particular reaction. Notice there's A moles of compound A plus B moles of compound B goes to C moles of compound C plus D moles of compound D. Well, this is how we write the Kc expression. Kc, notice that subscript as well, very important, is equal to, as I've mentioned, the concentration represented by means of square brackets, the concentration of the products divided by the concentration of the reactants. And that's equal to, there we have it, in the denominator, there we have our C, the concentration of C, and the number of moles is put as an exponent. So there's C moles of compound C, D moles of compound D, right? Those are the products, divided by A moles, there's the A moles there, of compound A multiplied by B moles of compound B, right? What is very important in connection with the Kc value and the Kc expression is we need to take into account the phases of matter that occur. You see, pure substances, liquids or solids, do not have a measurable concentration and are therefore given the value of 1 in the Kc expression, right? So liquids and solids are given the value of 1. That is correct. Homogeneous reactions. You may remember this term from grade 10. A homogeneous reaction is a reaction in which every compound exists in the same phase. So notice there's gas, 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 gas. These are all in the gaseous phase. We call them homogeneous reactions, right? These will certainly qualify for the Kc expression. Heterogeneous reactions. Well, we need to be careful when we see these. There's a solid, so it's going to get the value of 1 in the Kc expression. There's a liquid, it's going to get the value of 1. There's a gas, well, its concentration will certainly be taken into account in connection with the Kc expression. And there's an aqueous solution. That one's concentration will also be taken into account in the Kc expression as well. So a heterogeneous reaction is the opposite of homogeneous. Heterogeneous reactions are reactions in which the reactants and the products are not all in the same phase. Now, I'd like you to do the following for me. On the paper in front of you there, I'd like you to write the equilibrium constant expression for the first reaction. Let me take you through this. Here we have nitrogen gas plus hydrogen gas goes to, there's the reversible reaction signs, 2 moles of ammonia. You may remember from your grade 12 syllabus that this is the equation that represents the Haber process. For the Haber process, we get nitrogen, which comes to us from the fractional distillation of liquid air, hydrogen from the Sasol process, one can say, and the Haber process produces ammonia. How would we write the Kc expression for this? Well, very interestingly, this is the correct way to do it. Did you get it right? Kc is equal to, notice, the concentration of the products. Now, they're all in the gaseous phase, so therefore they all qualify. The concentration of ammonia and the 2 moles of ammonia there will be squared. There we have the nitrogen. There's only 1 mole of nitrogen there. So there we have the concentration of nitrogen and 3 moles of hydrogen. And there we have that there. Look at the next one. Here we have 1 reactant, but that's a solid. Ooh. And here we have a product that's a solid, and there we have another product, which is a gas. That will be taken into account. How will this Kc expression look? Notice we're going to have a 1 here, we're going to have a 1 and a 1. Well, the correct way to write this is Kc is equal to CO2 There we go. And of course, that is 1. So it's an understood 1 divided by 1. So all we're looking for there is the concentration of carbon dioxide. Our third one, here we have phosphorus, P4, that's solid, plus 6 moles of chlorine gas goes to phosphorus chloride. There we have it, PCl3, and that's in liquid format. Well, we know this gets 1 in the Kc expression. This gets a value of 1 as well. So how will we write the Kc expression for this particular reaction? Very interesting. Kc is equal to 1, there's the product, and Cl2, concentration of Cl2, and that is to the 6th power. That's how we write the correct Kc constant expressions for those reactions. Well done. How does Kc value change? Well, the Kc for a specific reaction is constant at specific temperature. Only temperature change the value of Kc. Only temperature. The value of Kc does not change if a catalyst is added, if concentration of the reactants or products change, or if the pressure of the system changes. Have you got that, grade 12s? So if you add a catalyst, if the concentration of the reactants or products change, or the pressure of the system changes, the Kc value will not change. Only the temperature will change the value of the Kc expression or Kc value. Now, let's understand what the value of Kc means. When Kc is equal to 1, as you can see on the monitor, what does that mean? It means this: the concentration of the reactants and the products are the same. You got that? When Kc is greater than 1, in other words, it's positive now, of course, greater than positive 1 for that matter, the concentration of the products is higher, the forward reaction is favored. Very important point. All right, you got that? When Kc is greater than 1, the concentration of the products is higher and the forward reaction is favored. When Kc is less than 1, the concentration of the reactants is higher and therefore the reverse reaction is favored. This is a very handy tool to keep in mind. So once again, Kc is less than 1 because oftentimes in the final examination, the examiners test our understanding of these important points. What formulae are used when doing Kc problems? Well, now we're going to take you right back to grade 10. You may remember in grade 10, you had a number of formulae that revolved around the number of moles. And one of the formulas, which is on the formula sheet, is C is equal to N over V. In other words, the concentration is equal to the number of moles divided by the volume. Now, grade 12s, we must recognize one important point here. The number of moles, the SI unit for that is MOL. And the volume is measured in cubic decimeters. So if you're given a volume in cubic centimeters, make sure that you convert that to cubic decimeters, because concentration has as an SI unit mole per cubic decimeter. Keep that in mind. What is the other formula that often plays off? It's this one here that says the number of moles is equal to the given mass divided by the molar mass. You may be saying to yourself, molar mass, where have I heard that before? Well, I'd just like to take you to the periodic table. I've got a periodic table right here. Let me just place it here. And let me just switch to this in a second here. There we go. Right, there we go. All right, so here's our periodic table. If you look at the periodic table, let's take, for example, carbon. There we have carbon here. Carbon is C on the periodic table. The number below, as you can see from the key that's given here, represents the atomic mass. It mentions that right here, okay, the atomic mass. And so when we look at carbon, the atomic mass for carbon is 12. that number is going to be used in calculating the molar mass of a compound. Take, for example, aluminium. There's its molar mass, 27. Here's another one. Let's suppose we had phosphorus just now, that P, there's its molar mass, 31. Or chlorine is 35,5. Have we got that, grade 12s? So remember to use your key here. Sometimes what the learners do, sadly, is they take the atomic number. It's not about the atomic number. We're calculating the molar mass. So therefore, we must rely on the atomic mass given to us on the periodic table in your question paper. Very, very important. So going back now to the monitor, here we have these formulae, and you may remember we were establishing this formula that said the number of moles is equal to the given mass divided by the molar mass. So I've just mentioned all these important points right here. Now we get to this important part of calculating the Kc value. And you know, I know that when the grade 12 paper is given out, for many learners, one of the first questions that they are interested in seeing what is waiting for them later on in the paper is what sort of Kc question have we got, right? And many learners feel that this is obvious. This is one of the toughest questions on the paper. It needn't be grade 12s. You know, if you practice, you will definitely succeed. And you know, in everything we do, plan your work, then work your plan. Now, let's go into our plan. For Kc calculations, you will either be given, notice the following, you'll either be given the initial amount in moles of the reactants. Notice that? You'll either be given that, or you'll be given the initial amount of one of the reactants and the equilibrium concentration of a reactant product. Well, thirdly, you could be given the initial mass of the reactant, the value of Kc, and the mass of unreacted reactant is also given. So they could give you any one of these three combinations, and therefore in your exam preparation, it may be very good to really accelerate your efforts in this connection. Make sure you come to a proper understanding of each of these three important ways, because they could ask you anything. Remember, they're testing your understanding. They're not trying to catch you out, testing your understanding. So what is our plan? Remember, we said plan your work, then work your plan. The three major steps to calculating the value of Kc. Number one, set up your Kc expression. Very, very important. Now, number two, use an equilibrium table. And so many textbooks call this the Rice table. Some call it the Ricee table, the R-I-C-E-E. We're going to talk about what that means. Now, thirdly, substitute into your Kc expression. Let's take these one by one. Firstly, set up your Kc expression. What we need to do there is we need to check the phases of our reactants and our products. Remember, liquids as well as solids get the value of 1. Gases and aqueous solutions, their concentrations are taken into the Kc expression. Next, we need to write down your Kc expression. So once you've had a look at your reaction, set up your Kc expression. How do you do that? Well, check the phases of your reactants and products, and secondly, write up your Kc expression. Point number 2, use an equilibrium or a Rice table. So the Rice table, we need to draw this up in this sort of format. What does the Rice table stand for? Here we are. Remember, we had this reaction early on. We had A, B, C, and D, right? Now, R stands for the ratio. In other words, the ratio or the mole ratio according to the balanced chemical equation, right? That is a very important point. The mole ratio according to the balanced chemical equation. The I stands for the initial number of moles. In other words, the amount of reactants before the start of reaction. How many moles? And they could give you this. You may remember, we actually spoke about this just now. So the initial number of moles. Then the change in moles. This is the most sensitive part of the RICE table. The change in the reactants or products based on the mole ratio. The E, the first E, stands for the equilibrium number of moles. In other words, how many moles of the reactant or the product were present at equilibrium. Very important. And then thirdly, the equilibrium concentration of the particular substance in the chemical equation, right? So if we got that, the I stands for the initial number of moles, to summarize. The C stands for the change in moles. The E stands for the equilibrium number of moles. And this last one here stands for the concentration at equilibrium of that particular substance there. Next, once we've got all of that organized, we need to substitute into our Kc expression. How do we do that? Well, we substitute into the Kc expression from step number 1. Let's have a look now at a worked example. This is drawn from paper 2, the October-November 2019. Believe it or not, it was last year's paper, question number 6. All right? And that question read as follows. Initially. Now that word is important. The word initially means at the start. Remember, in the RICE table, this will represent an I. Very important. Initially, 60,8 grams. Let's put the pause button there. Grade 12s, the examiner is not saying initially so many moles. He's now giving you a mass. So obviously he wants you to calculate something, right? So as you analyze your question, you need to look at every single word, every single expression, because this is going to help you come to a perfect answer in connection with your Kc value. So the question reads, initially 60,8 grams pure carbon dioxide. And it tells us the chemical formula for that is CO2, we know that, and it's in the gaseous phase. So therefore it's going into the Kc expression because it's a gas. Is reacted with carbon. Carbon is a solid. Carbon, because it's a solid, is going to get the value of, I can hear you saying it, yes, 1 in the Kc expression. In a sealed container, that is important because if any container is sealed, you may remember how we started our program this morning. What type of system are we dealing with? Open or closed? You're right. We're dealing with a closed system. And because it's a closed system, dynamic chemical equilibrium can be established. Not so? In other words, the rate of the forward reaction is going to equal the rate of the reverse reaction. Very important. Then it says of 3 cubic decimeters. We're happy about that because at least it's not in cubic centimeters and therefore we don't have to convert anything. It's already in the SI unit, which is great. This can take us places. The question continues. The reaction reaches equilibrium at a temperature according to the following balanced equation. Now, just a little detail. They may mention a temperature, right? That's there. Don't get flustered about that. Don't worry about that. Don't stress about that. All right? It will have to reach equilibrium at a certain temperature, but that temperature is never taken into account in our Kc calculation. So just park it right there. Here is the balanced equation. Let me ask you this question. What is the mole ratio for this particular balanced equation? I'll give you a moment to think about that. Have you got it? You're right. It is 1 mole is to 1 mole is to 2 moles. Remember you did that in grade 10? That's the mole ratio for this balanced equation. Just looking at this equation, we know that this, because it's a solid, in the Kc expression, is going to get the value of 1. This one is a gas, so its concentration will be taken into account. And this, because it's a gas, is also taken into account for the Kc expression. Now, Question 6.1 on that question paper said, define the term chemical equilibrium. What that question means is define the term dynamic chemical equilibrium. Do you remember what that means? Yes, you know you do. Here's the answer. It's the stage in the chemical reaction when the rate of the forward reaction equals the rate of the reverse reaction. Very important. Or you could say where the concentration of the reactants and the products remain constant. Grade 12s, that's a very important definition. Remember, the theme of our lesson this morning is chemical equilibrium. So therefore, when you go into the exam on that Monday, when you write paper 2, make sure you know the definition of dynamic chemical equilibrium. The next question, 6.2 read, at equilibrium, it is found that the concentration of CO2 is 0,054 mole per cubic decimeter. So notice they're giving us an equilibrium concentration of one of the reactants or the products. Calculate the equilibrium constant Kc for this reaction at the temperature T. And there we have 7 marks given us for that. Now, 7 marks does not mean that it is so difficult that it's 7 marks, as if to say that a 1-mark answer is very easy. No, no, no. 7 marks just indicates the extent to which we need to go to arrive at our answer. And grade 12s, all we need to do now, as we've established, is to plan our work, then work our plan. So how do we proceed from here? Well, point number 1. Here we have our chemical equation. Notice carbon solid plus carbon dioxide in the gaseous phase goes to 2 moles of carbon monoxide. There we have it. And that's in the gaseous phase. And the Kc expression for that, because it's only these 2 that come into play, is going to be the concentration of carbon monoxide, and that's going to be squared because there we have 2 moles there. And there we have carbon dioxide, which is there. And there's only 1 mole there, so that's an understood 1 here. We don't write it in because it's just like that. Okay. Next, we find the initial number of moles. Remember that equation, N is equal to M over capital M. That's the number of moles is equal to the given mass divided by the molar mass. Now, we need to find the initial number of moles of carbon dioxide. We were given the mass of 60,88, right? 60,88. I've got my calculator here now, and let's find the molar mass of carbon dioxide. Looking at the periodic table as well, let me just switch to this monitor here. So there I have my calculator right here. So as you know, carbon dioxide is CO2. So C is going to be carbon, it's going to be 12. So I say 12 plus, right? Oxygen is O2, right? I'm sure you can see that nicely. Oxygen is going to be O2. There's oxygen there. Oxygen is 16. So I'm going to put that in brackets. I'm going to say 2 times 16. I'm going to close brackets, right? Remember, that is CO2. And when I press equal to, there I get the answer. Can you see that 44? Yes. So the molar mass of carbon dioxide is 44 grams per mole. When we look back at the monitor now, you'll notice that's where this 44 comes from here. Do you notice, grade 12s, how you need to use your periodic table, how you need to use your calculator in conjunction with your question here? Well, when you divide these two, if you take 60,8 divided by 44 on your calculator, you'll get 1,382. And may I stress, please do not round up and do not round down. Remember, chemistry is very much like financial mathematics. Rather round off right at the end, because then you'll get the exact answer that is needed. Okay, so do not round off in the steps leading up to the final answer. At your final answer, you may want to round off to 2 decimal places or whatever instruction your question paper actually gives you. Moving on, the number of moles at equilibrium of carbon dioxide, right, is the concentration divided by the volume. Now, where do we get that formula from, you may be saying? Well, remember the other formula that we established was C is equal to N over V. So if you substitute into that formula, and that's the same formula that we're using here, the concentration they gave us as 0,054 divided by the volume, which is 3 cubic decimeters. Now our answer is 0,162 mole. So there we have the number of moles of carbon dioxide at equilibrium. Now, there's our rice table, all nicely set up for us. Notice there are only 2 compounds from that equation that qualify for the rice table. Firstly, it's the carbon dioxide and it's the carbon monoxide. Why? Because both of them are either in the gaseous phase or they're aqueous, right? Only those qualify for the rice table. Remember, the solids and liquids get the value of 1, so we just leave them out. Then the ratio according to the balanced chemical equation, as you can see there, carbon dioxide, there's 1 mole there, and carbon monoxide, there's going to be 2 moles there, right? Then we take the initial number of moles, we put that in here. We take the equilibrium number of moles, we put this here. Now let me ask you this question. Notice what we have here. We started with 1,382 moles of carbon dioxide. That was, as you know, a reactant, and reactants get used up. What was the value that was used up to bring us to the amount of 0,162? Well, by simple addition and subtraction, we get the values there. In fact, we're trying to find these out. So here now, we also have 0,162 divided by 3. We get that. And of course, there we have this here. And there we have that value 2,44, the equilibrium number of moles as well. So all pieces together. Remember, we calculated, or we were given the 0,054, right? In the question, they told us that. Okay, and then the equilibrium concentration, we calculated by introducing the volume. We take that equilibrium, and then we have this right here. So at the start, the initial number of moles is 0 right here. If you take here the equilibrium number of moles, 0,162, if you multiply that by 2, you're going to get the number 2,44. You may want to try that on the calculator. And the reason why we're multiplying it by 2 is because the mole ratio between these two is 1:2. So if this represents 1, then this must be 2 times that. And that's why we get that. So from 0 to 2,44, the number here is going to be 2,44. We know that because 0 plus 2,44 based on the mole ratio, which one should write here, will give you 2,44 moles at equilibrium. And then here, if you take 1,382, right, and you subtract 1,22, you're going to get this answer here, 0,162. Very important. So here we have all our values for our rice table nicely set up. Now we go to our third step, which is our Kc calculation. Remember, the Kc calculation is the concentration of the products divided by the concentration of the reactants. And we must not forget the exponent, the number of moles will go as exponents to each of those concentrations. And when we put that in, why, there we're going to get it. Here we have 2,44 divided by 3. You see, in other words, we're taking this here divided by 3, right? And that's going to be squared because there's 2 moles there, divided by 0,054. There we have it right here. And there we have that all squared. And finally, our Kc value is 12,24. Please note, grade 12s, that this particular constant does not have a unit. You know why? It's the ratio of 2 concentrations. That's why it does not have a unit. Right? The Kc constant is the ratio of 2 concentrations. concentration of the products divided by the concentration of the reactants. Now, question 6.2.2, based on what we've just calculated, the question said, calculate the minimum mass of carbon solid that must be present in the container to obtain this equilibrium. Well, the minimum mass would equal the change in the rise table. In other words, what reacted. So the mole ratio for carbon and carbon dioxide in that reaction is 1:1. I think we remember that. So M is equal to N multiplied by M, right? That's from that famous equation. And so when we take 1,22 multiplied by 12, right? Where do we get 12 from? Well, once again, let's just go to our periodic table because it's important for us to see these things all very nicely. If we take carbon, there's carbon here. Notice that's where we get the 12 from. The 12 represents the molar mass of carbon, all right? So that's where the 12 comes from there. Going back to the monitor now, here we see the following. There we have 1,22 multiplied by 12, and we're going to get 14,64 grams. That is the minimum mass that should be present in the container to obtain that equilibrium. That question 6 continued this way. How will each of the following changes affect the amount of carbon monoxide gas at equilibrium? Now we have to choose either increases, decreases, or remain the same. Grade 12, I want to suggest here, and I strongly want to stress, as a matter of fact, do not guess. What the examiner is doing in this part of the question is he's testing our understanding of chemical equilibrium. Notice he's shining the spotlight on one substance in that balanced chemical equation. In this case, it's on the carbon monoxide. And you may remember from the equation, the carbon monoxide is the product. There were 2 moles of carbon monoxide. So the question is, what would happen if more carbon solid is added to the container? What would happen to the amount of carbon monoxide? Well, the carbon is in the solid phase. We saw that. Only substances in the gaseous or aqueous phase will be affected by change in concentration. Therefore, the amount of carbon monoxide gas remains the same. That's the answer, right? So not long sentences like that. That's an explanation, a great explanation. There's no doubt about that. But the answer for 6.3.1 is it will remain the same. What's the reason? Well, there the reason has been furnished right there. Only substances in the gaseous or aqueous phase will affect changes to concentration. 6.3.2. If the pressure is increased by reducing the volume of the container at constant temperature, use Le Chatelier's principle to explain the answer. Well, we know that a change in pressure only applies to substances in the gaseous phase. So when the pressure increases, the system will try to reduce the pressure by favoring the reaction which has the smaller volume of gas moles. In other words, the lowest number of moles. Hence, the reverse reaction is favored, because in the reverse reaction, you may remember there's only 1 mole of carbon dioxide, but 2 moles of carbon monoxide. So the reverse reaction is favored, and therefore the amount of carbon monoxide, that being the product, will decrease. Very important. Then we have 6.4. The table below shows the percentages of carbon dioxide gas and carbon monoxide gas in the container at different temperatures. Notice the temperatures that are given here. We have 827 degrees Celsius, 950 degrees Celsius, 1050 degrees Celsius, 1200 degrees Celsius. Notice the temperature has increased. That's what those values are telling us. So when you see something like that, you must actually look at the trend, what's happening there. Well, look at the percentages. Notice here, the first one is 6.23%. Then we have 1.32%. Then we have 0.37%. Then we have 0.06%. Is that increasing or decreasing? You got it. It's decreasing in terms of percentages. Then we have our carbon monoxide. Our percentages, we have 93.77%. Then we have 98.68%. Then we have 99.63%. Then 99.94%. Notice there's an increase here in percentages. So have we got the trend? Here the temperatures are increasing. Here the percentages are decreasing. And here the percentages are increasing. Very important. So look at this question, 6.4.1, based on that table. Is the reaction exothermic or endothermic? You may be wondering to yourself, how on earth do I figure that one out? Well, it says refer to the data in the table to explain your answer. Notice, the reaction is endothermic since an increase in temperature favors the forward reaction. In other words, the product yield increases. You notice that? Favors the forward reaction. So an increase in temperature favors the endothermic reaction. Because the temperature was increasing, the endothermic reaction is favored. So the answer to question 6.4.1 is that reaction is endothermic. Question 6.4.2. Use the information in the table to determine temperature T. Show clearly how you arrived at the answer. You may remember at the start, they simply said at temperature T, that was the temperature. Now they want us to actually find that temperature. Well, how do we do that? To calculate the percentage of carbon dioxide gas and the percentage of carbon monoxide gas, we need to know the total volume first. Very, very important, right? We need to know the total volume first. So the total volume is at equilibrium is going to equal 0.162, remember that from the rice table, plus 2.44, right? Those are volumes there, and that's equal to 2.602 cubic decimeters. When we have that, well, the percentage of carbon monoxide will be 2.44 divided by 2.602 multiplied by 100, and there we have our percentage, 93.77%. Grade 12s, we want to stress that this PowerPoint presentation, as well as all the resources, are going to come to you, to your teacher, to your school. So if you feel we've been going a bit fast, remember you will have access to this, okay? And you can go back and have a look at this over and over and over again and come to an accurate understanding of this, all right? So very important. Check with your teacher or with your principal at your school, the PowerPoint presentation, as well as all the resources, the notes will be made available to you so that you can come to a proper understanding in connection with all of this, right? And therefore, looking at the temperature now, because that's 93.77%, here we look at our table, there we see our 93.77%, and if we look across there, that is mapped to 827 degrees Celsius. So notice a beautiful calculation here. You first have to find the percentage of carbon monoxide and then the temperature scale, and which percentage is that mapped to? 827 degrees Celsius. If our percentage was 99.63%, why then that temperature would be 1050. So that was a very, very nice question that was raised in last year's paper at the end of the good. Now we're going to go across to the May-June 2019 paper. We're going to have a look at question number 6. That question read this way. The balanced equation below represents the reaction used in the Haber process to produce ammonia. You may remember I spoke about the Haber process earlier on this morning. Now, in the Haber process, we have nitrogen gas. There we have it. 1 mole of nitrogen gas plus 3 moles of hydrogen gas is our reversible reaction, and that goes to 2 moles of ammonia. Notice this is a homogeneous reaction. In other words, all the reactants as well as the products are in the same phase. They're all in the gaseous phase in this particular case. And there we have the enthalpy value. In other words, our delta H value, or the heat of reaction, is less than 0. Now, you know from even grade 11 when you did exothermic and endothermic reactions, right? Delta H less than 0 represents the forward reaction is exothermic. Very important. So let's just keep that detail there. And as you work through this, just keep that in mind. Now they say in industry, the product is removed as quickly as it forms. Right? That's quite a very clever move, very smart of them. As the ammonia is formed, they take it out. More ammonia is formed, they take it out. Ammonia formed, they take it out. Now, 6.1 says, write down the meaning of the double arrow used in the equation above. Do you remember that from our lesson this morning? What is the meaning of this double arrow? Yes, you got it. That double arrow represents important information that relates to the reversible reaction. And this question goes on and on. I'm going to give you some time to work through this, right? Write down the meaning of the double arrow used in the equation above. Next, give one reason why ammonia is removed from the reaction vessel as quickly as it forms. And then the graph beside shows the percentage of ammonia at different temperatures, and it starts going into a Kc calculation. Let me give you a moment to have a look at question 6.1 and 6.2. Okay, try and answer those, and then we'll review them in a second. All right, write down the meaning of the double arrow as used in the equation above. You got that? The next one, give one reason why ammonia is removed as soon as it forms. Yes, right. Now, the double arrow, as you know, represents a reversible reaction. Right? You got that? Reversible reaction. And so both the reverse and the forward reactions can take place. In other words, the products can be converted back to the reactants. What about question 6.2? Give one reason why ammonia is removed from the reaction vessel as quickly as it forms. Well, to favor the forward reaction. In other words, the production of ammonia. Because as the ammonia is formed in the Haber process, they take it out, so more can be formed. They take that out, more can be formed. They take that out, so the story goes, which means better financial gain for the chemical company undergoing the Haber process, producing ammonia as well. Now, the graph beside, there we see the graph on the side, shows the percentage yield of ammonia at different temperatures. Let's just have a look at this graph. Notice the percentage yield. These are percentages. There's the 10%, 20%, 30%, 40%. What about here? This is pressure. 100 atmosphere, 200 atmospheres, 300 atmospheres, 400 atmospheres. And notice they've given certain temperatures here. That's at 500 degrees Celsius. This is at 450 degrees Celsius. And this is at 350 degrees Celsius right there. Right, so if we move on with this, notice now, they say write down the percentage yield of ammonia at 450 degrees Celsius and 200 atmospheres, right? So what's happening now is they want you to look at your graph and to try and map that out, okay? Let's see how that goes. There we go. Yeah, we come to this. There we go. Here we have our graph, right? With our questions. Our pressure is down here, and we have our percentage yield of ammonia on the y-axis. Thank you. All right, great. All right, so grade 12s, do you have any questions up until this point? Please feel free to write it down. I'm looking at the screen right here. Remember, as I stressed, that these resources will be available at your school through your teacher or the principal, right? So if you feel we've gone a bit too fast, well, you're not getting left behind, I can tell you that. You'll be able to look at it again and again and really help in preparing you for the final examination. Let's see, okay. Do we have a question? Let's see here. Nothing yet. Okay, fine. All right. So please feel free to ask any questions, okay? We're going to go on now, but if you have a question, we'll take that as well. Do I just continue here with that? Okay, right. So there we go. Can I put this one? It's easier for me. Or should I keep it on here? All right. Yeah. So you do. Click on the screen. Yes. You are organized. Is that right? Yes. Thank you. Right. So now let's keep moving on with this. The graph besides shows the percentage yield of ammonia at different temperatures and pressures. Here we have the percentages. I've been through that. And here we have the pressures right here. Question 6.3 says, write down the percentage yield of ammonia at, notice, 450 degrees Celsius. So let's find that on the graph. There's 450 degrees Celsius, this one here. And 200 atmospheres. So now we need to find 450. It's this graph here that we're dealing with. And where's 200? There's 200 here. So there's 200. And where does this meet? There it is right here. Do you notice? Right here where my pointer is. And now notice the yield going across there. It's 20%. Let's see that. There we go. That's the answer. Very nice. 20%. Next one. Refer to Le Chatelier's principle to explain how each of the following deductions are made from the graph. Notice the first one. For a given pressure, the yield of ammonia at 500 degrees Celsius is much lower than that at 350 degrees Celsius. So let's see on the graph what they're talking about. The yield. So first we're looking at the yield, right? 500 degrees Celsius right here. The yield is much lower here compared to this one here. How come? That's what that question is exploring. Well, at 500 degrees Celsius, notice this graph at the bottom here, 500 degrees, a much higher temperature than that one there. The forward reaction is exothermic. Remember that? Exothermic, the forward reaction. In other words, the reverse reaction is endothermic, right? That's the one that an increase in temperature will be felt. An increase in temperature favors the endothermic reaction. So the reverse reaction is favored. Follow that? Next, or we can say, looking at the other one, if you want to talk about the 350, because you see they mentioned two temperatures there, so you could choose to discuss that one, or as we've just done previously, the 500 degrees Celsius. At 350 degrees Celsius, there's a higher yield of ammonia. Notice a much steeper gradient, of course, and a much higher yield. The forward reaction is exothermic. The reverse reaction is endothermic. A decrease in temperature favors the exothermic reaction, and therefore the forward reaction is favored. I think you can tell that 300 degrees Celsius is much lower than 500 degrees Celsius. The higher temperature is 500 degrees Celsius. So therefore, this one represents an increase in temperature. So therefore, the endothermic reaction here will be favored. That one is a decrease in temperature when related to the 500 degrees Celsius. So therefore, the exothermic reaction here will be favored, and that is the forward reaction. Now, 6.4.2. For a given temperature, the yield of ammonia at 350 atmospheres is much higher than that at 150 atmospheres. Well, at 350 atmospheres, there's a higher yield of ammonia because an increase in pressure favors the reaction that produces the lower moles, right? In other words, the number of moles where you have an increase in pressure, the reaction that produces the lower number of moles is favored. Hence, the forward reaction is favored. Or if you want to discuss at 150 atmosphere, there's a lower yield of ammonia because a decrease in pressure favors the reaction that produces the higher number of moles. Hence, the reverse reaction is favored. What about question 6.5? A technician prepares ammonia by reacting 6 moles of hydrogen gas with 6 moles of nitrogen gas. Calculate the maximum number of moles of ammonia that can be produced for this reaction. Well, according to the balanced equation, 1 mole of nitrogen reacts with 3 moles of hydrogen. So in a real sense, to produce 2 moles of ammonia, right? That's the balanced equation in mole format there. Therefore, 2 moles of nitrogen will react with 6 moles of hydrogen to produce 4 moles of ammonia. So all we're doing is we are using the mole ratio concept of the balanced chemical equation to get the answer in this connection. And then moving on to question 6.5.2, the above reaction now takes place in a 500 cubic centimeter container. Ooh, that is not cubic decimeters. We must be wide awake to that. So the best way to convert this to cubic decimeters is to take that 500 to divide it by 1,000. That's how we convert from cubic centimeters to cubic decimeters. So 500 cubic centimeters, there we go. And at a temperature of 350 degrees Celsius and a pressure of 150 atmospheres. The system is allowed to reach equilibrium, which is lovely. Use the graph above and calculate the equilibrium constant case this reaction under these conditions, right? So here we have our solution. Step number 1, remember, plan your work, then work your plan. We first have to find the number of moles of ammonia. As you can see on the monitor here, number of moles of ammonia, you take 35 divided by 100 multiplied by 4, 1,4 moles. But even before that, let's get to our rice table. Here we have our compounds, nitrogen, hydrogen, ammonia. The initial moles, 6, 6, and 0. We were given that, one can say. Then, if we look at the equilibrium number of moles, we were told 1.4. There we have that 1.4 there. So we know at the start there was no ammonia there. So obviously, according to the mole ratio concept, that would give 1,4 right there. And if you use the mole ratio for these, why then you'll have this being 0,7 and this is 2,1 based on the 1-3-2 principle. That's the mole ratio of the Haber process for the balanced chemical equation. What does that mean for us? Well, 6 minus 7. We say minus because this is a reactant. It's being used up. 6 minus 0,7 will give you 5,3. 6 minus 2,1 will give you 3,9. And so there we have these two important values here, which are now taken to form our concentration. So if we have this 5,3, you may be wondering, how do I get 10,6 for this? Remember, according to the principle, if we just have a look here now, just go across here to this, down here. Right, I have 5,3. So there's a formula in chemistry that said to us that the concentration is equal to the number of moles divided by the volume, right? We may remember that. So remember now, the equilibrium number of moles was 5,3. So we need to find the concentration at equilibrium. So that's equal to 5,3. And we divided by, remember the volume? The volume was 500 cubic centimeters. So remember what I said, you take the 500 cubic centimeters and you divide it by 1,000, okay, to get cubic decimeters. If we do that, here's my calculator right here, to put it on the side there, I take my fraction button, in my numerator I put 5.3, in my denominator I'm going to put another fraction, 500 divided by 1,000, and there you'll notice I'm going to get 10,6. Can you see the 10,6? You may remember that from the rise table. So let's just write this down. That is equal to 10,6 mole per cubic decimeter. Mole per cubic decimeter. Okay, and that is going into our rise table there. What about the next one? 3,9. Well, we do exactly the same thing. Remember our concentration, just turn this way. Our concentration is equal to our number of moles divided by our volume. The number of moles that we've got there in the rise table already at equilibrium, the number of moles is 3,9. 3,9. And we divide that by the volume, which we've established already, 500 divided by 1,000, right? And the reason why we're doing this is because that is given to us in cubic centimeters. We can't work with that because the SI unit for concentration is mole per cubic decimeter. So when we use our calculator there, right, take our fraction button, in the numerator, we're going to put our 3.9, 3,9. In the denominator, we're going to take another fraction, we're going to put our 500, we're going to put our 1,000, right? And then we have our figure of 7,8. And you'll notice that that is the concentration at equilibrium. We're going to have a look at that on the screen right now. Right, that's our concentration at equilibrium. So we've got two figures here that we basically are concerned about, right? We've got 7,8 mole per cubic decimeter, and then we also have our 10,6 mole per cubic decimeter. What have we been saying, grade 12? Well, if we go back to the monitor here, just there we go. There we see now our entire situation right here. There's our 10,6. Remember we calculated that, right? There's our 7,8. Remember we calculated that as well. And the same can be true of this. We're going to find the concentration here. And we have 1,4 That's the equilibrium number of moles, and we divide that by the volume, then we have, that will work out to 2,8. We take these values now, we put them into our Kc expression. Remember, it's important to write your Kc expression. As we've established at the outset of our lesson, Kc is equal to the concentration of the products divided by the concentration of the reactants. Our product is ammonia. Our reactants are hydrogen gas and nitrogen gas. And then if we take these values here, there we have 10,6, there we have 7,8, and notice that is with the 3 because there's 3 moles of hydrogen that are needed for that. And there we have our 2,8, and there our Kc value is 0,02, right? Now, we're just going to address a question. We have a question here from Inkwenkwezi, and I'll read you their question. Their question says, we have a question regarding the Kc calculation. We know that it is important to consider the state of matter when calculating the Kc value. Well done, Inkwenkwezi. Our concern is as follows. Since only the concentration of matters in the gaseous and aqueous solution should be considered, what happens when you have hydrogen gas reacting with oxygen gas to produce water in the gaseous phase? Would the concentration of the produced water be considered in the calculation, and why? Yes. Here's the thing. Remember, water is an interesting substance. Water can be in the gaseous phase as well. All you have to do is just switch on your kettle and you prove that very clearly to yourself, right? That's called water vapor. It's called steam, one can call it that, and water can exist as a solid, a liquid, and a gas. So depending on your chemical reaction, it doesn't mean to say that water is this water that we get from the tap that's liquid or aqueous. No, it can also exist in the gaseous phase as well. And if it's indicated in the gaseous phase, well, then you take it into account in your Kc calculation. If it's indicated in the aqueous phase, you also take its concentration into account. If it's indicated as a liquid, it gets the number 1, simply put. And if it's indicated as a solid, which is in the case of ice in our fridge, well, then it also gets the number of 1, right? So the phase is important. You must just be guided by what is given in the question. Very interesting. All right, thank you for that question, Inkwenkwezi. I hope that clears things up. If not, please write another question and we'll handle it as well. Right, now, moving on, grade 12s. We've got a few minutes left for our program this morning. Here's another question. You may want to write this one down. This is from the October-November 2018 paper, right? Paper 2, so that's 2 years ago. The question read, dinitrogen tetraoxide. Oh, it's quite a mouthful for a Thursday morning. Dinitrogen tetraoxide. Oh my goodness. N2O4 gas decomposes to nitrogen dioxide, NO2 gas, in a sealed syringe of volume 2 cubic decimeters. So there they give us a picture of the syringe. And notice there's a decrease in the volume to that. The mixture reaches equilibrium at 325 degrees Celsius according to the balanced equation. Notice here we have one reactant and one product. Here we have the dinitrogen tetraoxide, gaseous format, and here we have the nitrogen dioxide. We are told that nitrogen dioxide, and it's true, that's a brown gas. And here we have the colorless dinitrogen tetraoxide. When equilibrium is reached, it is observed that the color of the gas in the syringe is brown. That's a very interesting point. Notice the brown is on the product side of things. Now question 6.1 says, state Le Chatelier's principle. Here's the definition that should appear, and this definition is found in the examination guidelines. The correct definition is this. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will cancel or oppose that disturbance. That's a very important definition. We should never come to a chemistry exam in grade 12 without knowing that definition and its application, of course. Now, question 6.2 says, the syringe is now dipped in a beaker of ice water. Now, we know ice water. There's a decrease in temperature. It's cold, right? So notice they're telling us that, but we must deduce that for ourselves. After a while, the color disappears, we are told. Is the forward reaction exothermic or endothermic? Explain your answer using Le Chatelier's principle. The answer is it's endothermic. Why? Because a decrease in temperature favors the exothermic reaction. The reverse reaction is favored, right? Very important. Or one can say the number of moles or the amount of concentration of dinitrogen tetraoxide increases, or the number of moles, the amount of nitrogen dioxide decreases. So to summarize, that is an endothermic reaction. What are our two reasons? Firstly, decrease in temperature favors the exothermic reaction. Remember, decrease in temperature, it was dipped in ice water. The reverse reaction is favored. And then 6.3, the volume of the syringe is now decreased while the temperature is kept constant. How will each of the following be affected? Choose from increases, decreases, or remains the same. 6.3.1 says the number of moles of dinitrogen tetraoxide. Right? Notice the volume of the syringe is decreased. Well, it will increase. What about the value of the equilibrium constant? The value of the equilibrium constant will remain the same, right? Because pressure, increase, decrease, has got no influence on that. And then thirdly, the rate of the forward or the reverse reactions, that will increase. Why? Well, that's what we learned this morning. Very important. They increase the reaction. Now we're going to conclude our program by looking at this calculation. 6.4. Initially, X moles of dinitrogen tetraoxide were placed in a syringe at a volume of 2 cubic deciliters. At equilibrium, it was found that 20% of the dinitrogen tetraoxide had decomposed. If the equilibrium constant, Kc, for the reaction is 0.16 at 325 degrees Celsius, calculate the value of X. Now, grade 12s, we need to set up our rice table. And remember what we learned this morning? Plan your work, then work your plan. Very, very important. If you do that, you can go to success. So how do we do this? Well, we format our rice table. Let's take this nice and slow. If you notice on the monitor, there we have our rice table. We have our two compounds. There's our dinitrogen tetraoxide. And there we have our nitrogen dioxide. We have our initial number of moles. We are told that there's X moles initially. There we are told that. We don't know what that is. We must find that. And we know that at the start of the reaction, the start of every reaction, there's no product that's formed. So therefore, we give that a 0. Then we have the change in moles, we have the equilibrium number of moles, we have the equilibrium concentration, and so the story goes. Right. So we are told at equilibrium, the constant is 0.16. So if we set up our Kc expression, Kc is equal to the concentration of the products divided by the concentration of the reactants, right? There we have the product, nitrogen dioxide. Remember, there were 2 moles of that, so therefore that's squared. There we have the reactant, which is dinitrogen tetraoxide. And so we have 0.16 there. And now going back to the rice table, let's fill in the rest of the rice table, seeing that we've got the first line of the Kc expression all organized. So when we come back to the rice table here, there we have it. Right. So we need to fill in the change in moles, and we need the equilibrium number of moles, and so the story goes. They tell us that at equilibrium, it was found that 20% of this compound had decomposed. 20% at this compound had decomposed. When we fill that in, we'll notice that X, right, that's 1X minus 0.2, right? This is where we get our 20% from, right? 0.2, 20% had decomposed. So if you take 20, right, divided by 100, right, you're going to get that. And there we take it from there. So we have 0.2x. And because this is in the ratio of 1:2, this is going to be 0.4. 0 plus 0.4x will give you 0.4x. X minus 0.2x will give me 0.8x. When I take this 0.8x and divide it by my volume, right, there I'm going to have this particular, remember the volume is 2 cubic decimeters. So you take 0.8 divided by 2, you're going to get 0.4x. That's a concentration, by the way. And there we have this also, 0.4 divided by 2, you're going to have 0.2. That's a concentration. When we take these values expressed in terms of x and put them now into the Kc expression, the concentration of nitrogen dioxide, right, which is our product, is 0.2x squared, and all of that. Algebraically, we will work to the answer of 0.16 moles. So those are very, very important principles. In connection with this rice table, notice it's also very important here now to put on the side of the rice table here that you are working with the mole ratio. You get a mark for that. Do you notice that? Very important. You must write that there, the mole ratio concept. In other words, this sensitive part of the table actually revolves around that. And then to find your concentration, you divide by 2 cubic decimeters. Very important. You also are honored with a mark in that connection there as well. So if we have to find the value of x for this particular one, the answer is 1.6 moles. I'm sure you'll agree that this is a very important calculation, and that is exactly how it should have gone. Okay, fine. So grade 12s, we have reached the end of our program now. We hope you have benefited from the program. There is another question we'd like you to try. This is from the May-June 2018 paper, question number 6, based on the principles that we've discussed, right? Very important. Work through these. Remember now, plan your work, then work your plan. What have we been saying in our program this morning? Well, to sum up, dynamic chemical equilibrium means when the rate of the forward reaction is equal to the rate of the reverse reaction. Remember the sign for reversible reaction, right? One arrow goes this way, the other one goes that way. All right, very important. Do you recall the 3 factors that affect the equilibrium position of a reaction? Yes, T, C, P. T changes to temperature, C changes to concentration, P, the pressure as well. Then do you remember the Kc constant? How do we find that? How do we write the Kc constant? Kc is equal to the concentration of the products divided by the concentration of the reactants. Very important. Remember that's a formula that you're not given on the formula sheet, so you must go into the exam knowing that formula, right? You can't find it on the formula sheet. It's not there. And then the other formulae that we discussed are very important. You could be given the concentration, or you could be given the number of moles. Remember that formula, C is equal to N over V. Concentration is equal to the number of moles divided by the volume. Or the number of moles is equal to the gas divided by the molar mass. Very important. So if you keep these principles together, and if you keep practice, if you work by that principle, you will do very, very well. Remember, chemical equilibrium is an important part of paper 2, and it's an interesting part. Many learners find it difficult, but it needn't be difficult if you are well prepared. Just ask yourself the question, what is this question asking me to do? And then in everything that you know, answer the question. We have every confidence, grade 12s, that you will do very, very well in your exam. But now you must really accelerate your efforts in preparing for your final exam. And so many times the learners do so much revision and preparation for physics on Friday, paper 1, that they neglect the chemistry part. And therefore they come out of the exam thinking, oh my goodness, that was such a difficult paper, but it was actually easy. So just keep preparing. We know that you will do very, very well in your exam. So keep working with this program and keep revising. Once again, if you found that there were certain points that you missed completely or you didn't understand, you will have the PowerPoint presentation, right? And you'll be able to consult that. You can go to the memoranda online as well, and you can check these things out so that you come to a proper understanding of this very important concept. We thank you so much for tuning into our program this morning. We just want to mention that the schools are asked to turn their mics on so that they can say goodbye. I just got a message in that connection. So I'll give you some time to do that, okay? I'll allow you to turn your microphones on and so that you can say goodbye, okay?
Bye, sir.
Bye-bye. I hope you enjoyed the program.